We made it to the last example of chapter 3. Yay! And hopefully you'll like this one. It's kind of a long one. It's got a lot of different parts in it. So let's get this one worked out. We're going to have carbon dioxide that is contained in a piston cylinder assembly. It's initially at a pressure of 6 bar, a temperature of 400 Kelvin, and it undergoes an expansion to a final temperature of a mere 298 kelvins, during which we know pressure times volume to the power of 1.2 is equal to a constant. Polytropic relationship here. Assuming an ideal gas model, we are going to find final pressure, work, heat transfer. Notice the units here. We got kilograms in the denominator. Now, let's see if we have any keywords we really need to pay attention to. Not too much here. We got an expansion term. We've got our values. Obviously, those are important. We've got this. Notice N is 1.2, and it says we have ideal gas. So pay attention to the ideal gas because that gives you some equations. Now, remember, since we have an ideal gas, let's go ahead and write down the equations that we can use. And to do that, let's see what we want to find. We want final pressure here. So if we want final pressure here, we want to use an equation that has pressure in it. So let's use T2 over T1 equals P2 over P1 to the power of N minus 1 over N. Right, so that's an expression we developed it in the last video when we were talking about the polytropic process with an ideal gas. Now, N, remember, is going to be found right here in this relationship. So N is going to be 1.2. So that's usually going to have to be given to you. Now we have everything we need to plug into this equation to find final pressure. So let's do that. So T2 over T1, we're going to get 298 kelvins over 400 kelvins. And then that's going to equal P2 over 6 bar, because P1 was our initial pressure. And then our exponent here is going to be 1.2 minus 1 over 1.2. So P2, our pressure at the final state, is going to be 1.026 bar. Now let's see if that number makes sense relative to the scenario we've got. We've got this piston cylinder. It's initially at a pressure of 6. It says it undergoes expansion. Now, if we're undergoing expansion, that means the volume is going to increase, which means the pressure should decrease, and that is exactly what happened. We started at 6 bar, now we're at 1.026. So it did decrease, so at least it went in the right direction. So that's a good sign there. Now let's move on to parts B and C. Let me switch pages here. Now for part B, we are wanting to find work. And remember, we want it in kilojoules per kilogram. And we're also wanting Q. Don't forget that Q. Now remember, anytime we want to find work and Q, you're going to go back to what equation? The energy balance equation. Hopefully you said it with me. Energy balance. That's the one you want to go back to. When in doubt, go to energy balance. And that equation is delta KE plus delta PE plus delta capital U equals Q minus W. We didn't hear anything about any velocity, so let's get rid of that. And we didn't hear anything about an elevation change, so let's get rid of potential energy. That's going to leave us with delta U equals Q minus W. Now, notice this is capital U. All of the information we usually get is usually the little u, the specific internal energy. So let's write our relationship between internal energy and specific internal energy. We know delta U is going to equal the mass times delta little u. Now let's plug this into our equation. So we'll get M times delta U equals Q minus W. We've got this mass here. Let's go ahead and divide through by that mass. So that gives us delta U equals Q over M minus W over M. This is our new equation. Now look at that and think about the units. What are the units going to be here for these two terms? Q and W are usually kilojoules. Now we're dividing by mass. So that's going to give us kilojoules per kilogram, which is exactly what units the problem is asking for. So that's perfect, right? So we did a good job there. Now let's keep going. We need to find work. And the way we find work with a piston cylinder assembly is going to be to use this integral equation that we keep seeing over and over again for closed systems. So this will be it, and we have to have an equation for pressure here. Now we know the relationship is PV to the power of 1.2 equals a constant, so that's what we're going to use to find an expression for pressure. So let's write down that expression. Let's solve this for P. So P is going to be the constant over volume to the power of 1.2. We're going to take this, plug it into the equation here. So we're going to get the integral. We're going to integrate from volume 1 to volume 2. This is a 2 here, it's hard to tell. And the equation for pressure is going to be C over volume to the power of 1.2 times dV, where V is volume. Now C is a constant, so you can move that to the outside. And then when you integrate, what you're going to get is work equals C times V to the power of negative 1.2 plus 1 over negative 1.2 plus 1. And then we need to evaluate that at V1 and V2. All right, so do a little calculus there. Now, before we can move forward, we have to figure out what C is. We can't just leave this C here. All right, so let's figure out what C is going to be. And then we'll go through and plug everything in. So C is going to come from up here. And we know that we can write C is PV to the power of 1.2. So essentially at each state, we could say P1 times V1 to the power of 1.2 is equal to P2 V2 to the power of 1.2. Okay, so we'll use these relationships here. Notice when we're integrating, doing our limits here, we have state 2 properties and we have state 1 properties. So when we plug this in for C, we'll have that work is equal to P2 V2 to the power of 1.2. That's the C term, times V2 to the power of negative 1.2 plus 1. Then we subtract the same term but for state 1. So now I'm going to use this C value here just to keep everything at state 1. So we get P1 V1 to the power of 1.2 times V1 to the power of negative 1.2 plus 1. And put that over negative 1.2 plus 1. Okay, so now we have that. And keep in mind, since this constant is PV to the 1.2, it's always equal to a constant. You don't necessarily have to separate these out for each of the states. That's just how I happened to do it in this case. We didn't do it like that in the other problems, but here that's how I chose to do it. So now if we go through and simplify all of this, what you're going to end up with, if you look, we've got v2 to the power of 1.2. We also have v2 to the negative 1.2. So those are going to go away. So that's going to leave us with p2 v2 minus p1 v1 over negative 0.2. Now we're stuck with this. So this is work, an equation for work. We don't have any volume information though. Nothing was given to us about volume. We have no idea anything about that. So no V info. That means we're going to have to use the ideal gas law. We were told to assume an ideal gas model, so let's make use of that. There's the equation. This is specific volume. So V, remember, is regular volume over the mass. Let's plug this into here. And we'll get pressure times volume over mass equals RT. And notice we've got the product of pressure and volume here. So let's get the product of pressure and volume using this expression. So PV is going to be equal to MRT. And now let's make this substitution. All right, and once we do that, we're going to have W equals MRT2 minus MRT1, and we're going to put that over the negative 0.2. So it's looking good so far, right? Now, we've got this mass here. Remember the units we need for work. We want kilojoules per kilogram. We need mass in the denominator. So we've got this M here. Let's make use of that. Let's divide through by M. That'll give us W over M. That's going to equal R, which is the same for both states, times T2 minus T1. Put that over negative 0.2. Now we're to the point, finally, where we can plug in values. We have both of these temperatures. We can find R using the tables, and then that will allow us to solve for work per mass. So using the values, we're going to have R bar. Remember, this is R bar over molecular weight. R bar is going to be 8.314 in the SI system. And molecular weight will be 44.01. Units you get after you do all the units will be kilojoules, kilogram, Kelvin. Multiply that by the change in temperature, so that'll be 298 for temperature 2 minus 400 for temperature 1. Those are both in kelvins. Then divide this by negative 0.2. Almost done. So now simplify all this. Pay attention to your units. Kelvins go away. You are left with kilojoules per kilogram. Exactly what we wanted. So now W over M is plus 96.3 kilojoules per kilogram. So now we got part B done. Took us a while to get there, but we finally got it. And the last thing we need to do is find the answer for part C, which is to find Q. All right, so the energy transferred by heat. So Q equals something. We got to figure out what it is. Let's look at the equation we have. We already established before that delta U has to equal, actually I drew that there, has to equal Q over M minus W over M. So we've got that. We found W over M, and if we can find delta U, then we'll be able to solve for this, right? And really, let's revisit this. I wrote this down without thinking about it. We want kilojoules per kilogram, so really we want Q over M. Notice that's what we've got here. Isn't that convenient? Now, we're going to use a table to find this. And this is going to be table A23 in the Moran book. Okay, so we're going to use that table. And what this table gives you is your ideal gas properties for certain substances. All right, so this example was, I can't even remember, I think it was CO2, right? I can't even remember. Yep, CO2. So carbon dioxide was our substance. So in table A23, if you have the book, you can look at that table and this is what it gives you. It's got all of these substances here. It's got temperatures in kelvins. There's also a similar table in English units. And we've got H, U, and then we've got S, which that's entropy we'll talk about later. Notice there is a bar over these terms. We haven't seen that before. Now, what this bar is telling you, it's telling you something about the units. If you look up here, it's giving you the units. It says enthalpy and internal energy is given in kilojoules per kilomole. So here is that kilomole coming again. Now, we got to figure out what to do with that. Okay, but this is the table we're going to use for the ideal gas properties. All right, so A23. And let's make a note about what we just said about the kilomole. So the table gives U bar, which we said was kilojoule per kilomole. Remember that molecular weight is kilogram per kilomole. Now that means I just want to get kilojoules out of here. So what we're going to do is we're going to divide, whoops, that's not a D. We need to divide by molecular weight. So we're going to have Q over M equals U bar at T2. Okay, this is supposed to be T2. I'm not sure what happened there. T2, and then we're going to subtract U bar at T1. And then we're going to divide that by our molecular weight. And then we're going to plus Wm. So essentially what we did, we started with this equation. I solved it for Q1. So I moved this to the left, moved everything else over. And once you flip all the signs around and everything, this is what you're going to end up getting. Our table gives us U bar. So to get U, I'm going to take U bar and I'm going to divide by molecular weight. And you'll see how this works out when we write out all the units. Let's plug all of our values in. We're going to get Q over M. U bar at T2 is 6885. So our temperature was 298. So here is 298, 6885. Okay. And let's put that on here. And then we're going to subtract the U bar value at T1. T1 was 400. So you just look on this table. Only takes a second. Here is your U bar number. So 10,046. So that'll be the next number. And these are both kilojoule per kilomole. Now we're going to divide those by molecular weight. So for carbon dioxide, molecular weight's 44.01. That's kilograms per kilomole. And then we're going to add W over M, which is 96.3 kilojoules per kilogram. Now let's do our unit check, make sure it looks right. So we've got kilojoules per kilomole over kilogram per kilomole. These kilomoles cancel out. Now we have kilojoule per kilogram, which is perfect because that's what we need to add to this term. Just what we wanted. Last thing for chapter 3. Let's write the answer. So Q over M is going to be a positive 24.47 kilojoules per kilogram. And there we have it. We've finally finished. All right, so hopefully you enjoyed that problem. It was a lengthy one, had a lot of different stuff in it, but hopefully it gives you some good ideas on how to solve problems. All right, that's the end of chapter 3. I am excited about chapter 4. We will finally get to have mass flowing in and out of our systems. If you thought these problems were long, chapter 4 is not going to be fun for you. I'll warn you now. All right, guys, I will see y'all later. Y'all have a great night.